A p-value answers one very specific question. If a particular assumption about the world were true, how surprising would this data be? That assumption is called the null hypothesis. The null hypothesis is not what you believe. It is a working claim you temporarily assume in order to do a calculation. Most of the time, it says nothing interesting is going on. No effect, no difference, no association. Once you state a null hypothesis, you collect data and reduce it to a single number called a test statistic. That number measures how far your data are from what the null hypothesis predicts. Bigger departures mean more tension with the null. Now comes the key step. You imagine repeating the experiment over and over in a world where the null hypothesis is actually true. In that world, the test statistic would vary randomly from sample to sample, forming what's called a null distribution. The p-value is the probability, assuming the null hypothesis is true, of getting a test statistic at least as extreme as the one you observed. At least as extreme matters. You don't just ask about the exact result you saw. You also include results that would have looked even more incompatible with the null. The p-value is the total probability of all those outcomes. So if the p-value is small, the data would be rare in a world where the null hypothesis is true. That makes the null look implausible. If the p-value is large, the data are not unusual under the null, so you don't have strong evidence against it. Here is a concrete example. Suppose the null hypothesis says a coin is fair. You flip it 20 times and see 14 heads. Under fairness, you can compute the probability of getting 14 or more heads. That probability is the p-value. If it's small, the result would be surprising for a fair coin. If it's not small, the result is well within the range of ordinary randomness. In practice, people compare the p-value to a pre-chosen cutoff called alpha, often 0.05. If the p-value is below alpha, they reject the null hypothesis. If it's above alpha, they fail to reject it. This rule controls long-run false alarms. If the null is true and you follow this rule repeatedly, you'll falsely reject it about 5% of the time when alpha is 0.05. Now, what p-values do not mean is just as important. A p-value is not the probability that the null hypothesis is true. The calculation assumes the null is true from the start. It never assigns probabilities to hypotheses. A p-value is not the probability that the result happened by chance. Randomness is already built into the model. The p-value is a probability about data under a specific assumption. A small p-value does not mean the effect is large or important. With enough data, even tiny, meaningless effects can produce very small p-values. And a large p-value does not prove there is no effect. It may just mean the data are noisy or the sample is small. This sensitivity to sample size is crucial. Many test statistics divide an estimated effect by its standard error. As sample size increases, the standard error shrinks, making the test statistic larger and the p-value smaller, even if the effect itself barely changes. That's why p-values should be paired with effect sizes and confidence intervals. A confidence interval shows the range of effect sizes consistent with the data. For many common tests, a two-sided p-value below 0.05 corresponds to a 95% confidence interval that does not include the null value. Finally, p-values only make sense relative to their assumptions. They depend on the chosen model, the test statistic, and the analysis plan. Violated assumptions, multiple testing, or flexible analysis choices can make p-values misleading. A safe way to say it is this: assuming the null hypothesis and the test's assumptions are true, the probability of observing results this extreme or more extreme is p. That's all a p-value is. No more and no less.